So this will be a continuation class of what we have discussed regarding Laplace transforms. And our focus now is finding the solution of constant coefficient linear ordinary differential equations using Laplace transformation. So allow me to share the Jamboard where I wrote already the formula for Laplace transforms of derivatives. Now you could see here the Laplace transform of the first derivative of the function, and it's s times the function of s minus f of 0. The second derivative will have s squared function of s minus s f of 0 minus f prime of 0. You have the third derivative, s cubed function of s minus s squared function of 0 s f prime of 0 minus f double prime of 0. And for this Laplace transform of the fourth derivative, you have s raised to 4 times the function of s minus s cubed f of 0 minus s squared f prime of 0 minus s f double prime of 0 minus f triple prime of 0. The reason why I wrote this one, although you get to see in the slide that was shared to you the formula for the Laplace transform of the first derivative and the second derivative, is for you to see the pattern in the formula of Laplace transforms of derivatives. So these are the things that is worth noting. All the terms that follows after the first term are separated by minus sign. So they are all separated by minus sign. All the terms have decreasing exponents in s, so s1, then s raised to 0, which is understood to be 1, s squared s, s cubed s squared s raised to 0, s to the fourth, s cubed s squared s, and s raised to 0. So decreasing an exponent of the s. The first term will start with an exponent equal to the order of the derivative, and it will be multiplied by the function of s, since we are given here the function of t. The second term will also have an s, but the multiplier is the function of 0. Not the function of s, but the f of 0, meaning you evaluate the function when the time is 0. After this f of 0 terms, the rest are derivatives of their function evaluated when t is equal to 0. So we start with the first derivative. Then if there's a need for us to add the second derivative or the third derivative, we may do so. As long as we end with the last term in which the derivative of the function evaluated as 0 has an order which is 1 less than that of the given derivative. Okay? The order is 1 less than that, the order of the given derivative. So those are the things that you could see here in the formula of the Laplace transforms of the derivatives. Knowing the pattern does not require you anymore to memorize in toto each of the individual formulas. So I hope you got the pattern as explained already. So we will transfer now to our slide and go back to where we left up on our last discussion. So in our last discussion, I think we were discussing the inverse Laplace transform. We're in the process of method of partial fractions was covered. Okay, so this is what we ended, I think. So now for our application of Laplace transforms of the derivatives, we will go to specific applications already of the Laplace transforms of the derivatives, the Laplace transform of basic functions, and the inverse Laplace transform of a function of s. Now, in the table that was shared to you in here, what will only be covered in here in the introductory part of Laplace transform is the Laplace transform of the derivative and the first shifting property of Laplace, which is part of the 10 formulas shared to you, okay, for the Laplace transform of basic functions. For these theorems, the initial value theorem and the final value theorem, this one, the second shifting property, this will be covered already in your advanced engineering mathematics together with the Laplace transform of the integral of your function evaluated from 0 to t. So our goal is just the application of Laplace transforms of derivatives and the first shifting property in finding the solution of constant coefficient linear ordinary differential equations. Okay? Now, let me clear my markings. So what we will do now is go to the specific example. This one are formulas that were covered already. This one now is how we perform Laplace transformation on the individual terms in our DE. That way we can find its solution. So you perform Laplace transformation on the second derivative. This is it. You perform Laplace transformation on the first derivative and Laplace transformation on the unknown function together with the function here on the right side of the DE. This is the formula for second derivative Laplace transform. This is the formula for the first derivative Laplace transform. Getting the Laplace transform of y would simply be y of s. Generally, that's how it's represented. And Laplace transform of your function generally is presented by f of s. Your goal after doing this is to isolate the y of s on the left side of the equation and come up with an expression equivalent to n of s over d of s, which you can invert. Okay? Of course, this is invertible if the functions that were given to you are within the 10 that was given to you in the formula. Okay, so when you invert this particular expression, the first thing you do is check the factors of your denominator. Now, after inversion, the answer to this y of s, which is actually, if you invert y of s, you'll be getting y of t, and you will have here a function of t. This is already the answer to this particular general form of your higher order DE using Laplace. Okay? Let me clear my marking. So if you do that, if you use this particular procedure here, this is your DE, and this is the initial condition. If you apply Laplace transformation on all the terms in your DE, you will have Laplace transform of the first derivative, 2 times the Laplace transform of y and Laplace transform of 12. The Laplace transform of your first derivative actually is s, y of s minus y of 0, right? That's the Laplace transform of this first derivative. What is y of 0? That's 10 here. We call this the initial condition that is provided together with your DE. So the reason why you see a minus 10 here, because your y of 0 was already replaced by the value of it as provided in the DE. So it's minus 10, and you have here 2y of s, and you have here 12 over s, because the Laplace of a constant is 12 over s. Now you need to isolate the y over s, the y of s here. So you see this one, it's isolated here, and its factor is 2, is s rather, for this, and 2 for this one. The 10 here, since you want to isolate the terms containing the y of s only on the left side, the 10 has to be transferred here. Now if we keep y of s here, we need to divide the entire equation. So we divide this entire equation by s plus 2. So now your 10 will be divided by s plus 2, and your 12 will be divided by s plus 2 as well. So now it has 2 factors in its denominator, the s and the s plus 2. Now this one is invertible. This one will use the method of partial fractions. So if you do that, if you use method of partial fractions here, that would be 12 over s times s plus 2. And you can have any letter here you want to represent your coefficients. You can interchange these two as well. But we get A1 and A2 based on the techniques discussed already in calculus and in method of undetermined coefficients. So the value is 6 and -6 for A1 and A2 respectively. Now the 10 over s plus 2 was copied from here. And this 12 over s times s plus 2 was replaced already by the sum of its equivalent partial fractions. So, ari na sila nga duwa. So, you have 10 over s plus 2 and you have here 6 over s and -6 over s plus 2. We combine the 10 over s plus 2 and -6 over s plus 2 to give us 4 over s plus 2. And after inversion, you will have this as your answer. Okay, that's it. So you only perform inverse method of partial fractions to this one. This one can be inverted right away. Okay, now let's say if we have the same left side, but we change the right side to the sign. So the Laplace transform of the sign is omega over s squared plus omega squared, or the constant that appears in the argument of your sign. So you have 4. So this is 16. This one is the same as the one that we have in example 11. So this one will still be sy of s minus 10 plus 2y of s. We isolate the y of s here, so we need to divide this entire expression by s plus 2. So you have a 10 which is transferred here, so that would be 10 over s plus 2. And you have a 48, this one a 48, s squared plus 16, and you have another one which is s plus 2 due to the division by s plus 2 on the left side. Now, you don't need to use partial fractions here. You only need to use partial fraction in this side. So this is your linear factor, and this is your quadratic factor. As learned in the past, previous lesson, if you have a quadratic factor, there should be 2 coefficients in the numerator. One which is a pure coefficient, in this case that's b sub 2, and another one that has the s. After you have correctly written your equivalent partial fractions to this original fraction, which you need to invert using the method of partial fractions, you just find the values of the coefficients a, b sub 1, and b sub 2. After you have done that, you substitute it in your 3 partial fractions. And by the way, having said partial fractions 3, you see this one, the original function of s, the degree in the denominator, which is s cubed, dictates to you how many partial fraction equivalents should be equated to it. So how many partial fractions should be added? That way it would be equivalent to this. So in this case, you have third degree, so you should have 3 partial fractions. So in this case, you will be seeing here 3 as well. This one is the one that does not need the method of partial fractions. This already, these are the sum of the partial fractions equivalent to the original expression, this one. Okay, so this one has a denominator, which is s squared plus 16, another s squared plus 16, yielding either a cosine or a sine, depending on what's in the numerator. So this is an s, so it's a cosine. This is a constant. So if this is a constant, the constant that should be written here is your omega here. So it should be 4. So if you factor out 4 from 4.8, that would be 1.2. So that is why you only are left with 1.2 sine of 40 for this one, because you use the 4. That way you can have the complete function of s for the sine of 40. For these two, since they have the same denominator, you need to combine. So that would be 12.4. And anyway, the inverse of this s plus 2 in the denominator is just an exponential function, which is e raised to minus 2t. Okay? So this is already the solution of this particular differential equation using Laplace. Now, the first two examples were first order. Let's try something that is higher order. This one is second order already. If you will apply Laplace transform to the second order derivative, this will be its Laplace transform. S squared y of s minus s y of 0 minus y prime of 0. For the first derivative, s y of s minus y of 0. I'm using already the formula that was shared to you in the Jamboard for you to see the pattern. If we substitute the condition here, the initial conditions provided, y of 0 is 10. So automatically, this is 0. And this is 0. Y of 0 is, sorry, this is 10, by the way. And it's the y prime of 0, which is 0. So this is the one that is 0. So then, this one is s squared y of s minus 10s because your y of 0 is 10 and you have your 0. Here you have also 10, so you have s y of s minus 10 and it's multiplied by 3. You have here 2y of s for the last term, okay? Laplace of y is y over s. Laplace of 24, excuse me, is 24 over s. Now, if you will isolate the y of s expression here on the left side, if I clear the markings so that we'll not have everything there topsy-turvy. So you keep this one, and this one on the left side. The rest should be transferred here. So what will be transferred here is 10s and 30. So you see this at 10s and 30. So why do we have this divisor and added divisor? This is an s only for the 24. Why have this and this? It came from the factor of the y of s here because if you isolate y of s on the left side, its factor is s squared coming from here plus 3s from here, and we have plus 2. So you keep only the y of s here, so you need to divide the entire equation by s squared plus 3s plus 2. So that's the reason why you see an s squared plus 3s plus 2. When you do inversion class, you check first whether this quadratic factor is factorable, and it is. So it's written like this and like this. So this first part is our y of s in the previous example. So we know already its corresponding y of t. So we need only to process this one. Okay, ini na lang ang nabilin kay ini siya may-ari ta ni equivalent expression sa previous. So we just use that one. So let's call up this 24 over s times s plus 1 plus s plus 2 is this already from our previous example. And this will be our coefficients for it. And just in case you wish to practice again, you can get the coefficients A, B, C for this particular fraction when these are the partial fraction equivalents. And we'll have another partial fraction for this one. And this would be it. I think different galit siya ang previous example. So this would be the partial fraction equivalent for this one. And the partial fraction equivalent for the second is this. So combine the fractions that have the same denominator. So in the case of s plus 1, you have minus 24 and 20, so minus 4. In the case of 10 and 12, negative 10 and 12, so that would be 2. So copy the denominator for 12 over s, it's as is. So this is already your answer when this is inverted. Okay? Actually, it's a repetitive pattern, but you make sure that before you do method of partial fraction, make sure that you have properly factored your denominator. For this second order, DE, so you also perform Laplace transformation to the second order derivative. So this is your condition. This is for the second derivative, and this is for the 5y. Okay? Substitute the values of the initial condition. So this would be it. When you isolate the y of s on the left side, this will be the resulting expression, and that requires that your right side expression will be divided by s squared plus 2s plus 5. Coming from here, this is s squared, this is 2s and 5. So for this one, there's no need for method of partial fractions because you can readily have this inverted using completing the square. But this one will need you to perform method of partial fractions because of the s. This one will have the sum of 3 partial fractions. So 1 for the a over s for this, and 2 for the bs plus c for the second one, or the as plus b for the second one. If you find a and b using the methods discussed, you will have a equal to -4 and b equal to -8. So if you substitute -4 and -8 for b and a, so you have it here, you copy the 4 over s that we have here. You can have this inverted by completing the square. But before you do that, since they have the same denominator as our second term here, which we did not touch using method of partial fraction, then first combine. So you have 4 over s in here, and you have minus 4s, -8 plus 10 is plus 2. So same denominator for the 2, so you have this one. Completing the square of the denominator requires that you add 1 to s squared plus 2s. And since you have 5, of course, you need to add 2 squared to make it 4 plus 1, that would be 5. Now, this is the sum of 2 perfect squares that will appear now in your denominator. And this is your denominator. Just like what we did in the previous discussion on completing the square for inversion, you have to copy the shifting in the denominator and reflect the same shifting in the numerator. So this is the same shifting here. And since you have a multiplier of -4, this should also have a multiplier of -4. Now this becomes -4s minus 4. The original expression is plus 2. So what will you add with -4 to make it plus 2? So that would be plus 6. So 6 minus 4 is plus 2, this one. So make sure that when you manipulate, you still have your original DE. Or rather, your original fraction part, whether it's numerator or denominator. So in this case, you have this. Now, this is your perfect square already. So this is for the cosine. The shifting of the cosine because your s has plus 1. So then you account for it by introducing the exponential function e raised to minus t. The 2 in here dictates what constant should be present in the argument of the cosine. The 4 constant here, the -4 was just copied. The inverse Laplace of the 4 here over s is just the 4. Now remember, you have to add here 6 to -4 to make it 2. But what you need in the numerator constant is just the 2. Since if it's a sine, it's only the omega that should appear in the numerator. So you have here a 2 in the numerator. So 2 because of the omega, which is 2. So what is left, not needed in your function of s, is the 3. So you have 3 times the function of t after you have inverted 2 over s plus 1 quantity squared plus 2 squared. Now, if you wish to know whether, recheck whether your solution for the DE is correct, this one, have this Laplace transform. Meaning you perform Laplace transformation here and check whether it will be the same as this one. If it's the same as this one, as long as you did the correct substitution of Laplace transforms of derivatives in the original DE here, and that of your function together with the substitution of the initial conditions, then your answer for the solution of your higher order DE is correct. Okay? So when you find the solution of a differential equation using Laplace, it's important that you know how to apply Laplace transforms of derivatives. Then apply Laplace transform of functions. Then use the method of partial fractions in the process of inverting your function of s in the form of n of s over d of s. So what's the tool? You use the method of partial fractions. Okay, so that ends our topic on the application of Laplace transformation. This is the introductory part only to solution of constant coefficient linear ordinary differential equations.